Good. We shall start. It's 1 p.m. in Singapore. Welcome everyone to the workshop about Open Graph Benchmark, large-scale challenge, which was a part of KDD Cup this year, 2021. My name is Jure Leskovec, and I'm one of the co-organizers of this KDD Cup. My other collaborators, co-organizers are Wei Hua Hu, Matthias Fei, Hongyu Ren, Maho Nakata, Xiao Dong, and myself. What I want to do in these opening remarks is give a bit of a context around how we went about creating this benchmark and this challenge, review the results, and then discuss the agenda for the rest of the day. So graph machine learning, representation learning on graphs, graph neural networks is one of the hottest areas in machine learning right now. About a year ago, we've been asking ourselves how can we help further move the progress in this exciting area. So in May of 2020, we presented what we call OGB, Open Graph Benchmark, which is a realistic and diverse benchmark data set for machine learning with graphs. And we released it at ogb.stanford.edu. And this benchmark contains 15 different data sets on different machine learning tasks: node property prediction, link prediction, and graph classification. And data sets are of various sizes and come from different domains, from natural sciences, social sciences, as well as kind of information. This benchmark received a lot of positive response. And in a year, we received over 300 different submissions. And over time, really drastic improvement has been made on these different data sets. New architectures were developed, and it was really, or it is, really awesome, and we were very, very happy we were able to help the community. Here I show for two different data sets that are part of OGB, how the performance of the best submission is increasing over time. However, we also realized that there is need for a large-scale benchmark, right? To basically yield breakthroughs in graph machine learning, we need a large-scale data sets. We need a large-scale background graph. And for this, we decided that machine learning on large-scale graphs is another place where we want to invest and basically create a common benchmark where, again, community can develop methods. And this is for two reasons. First is that this will push forward the field. The second one is that it both presents interesting machine learning challenges, but also interesting systems challenges because of scaling up. Machine learning on graphs is very challenging, or kind of more challenging than in other domains. So because of these reasons, we decided to release the large-scale benchmark. So this came, and in February this year, we released what we called OGB-LSC, so OGB Large-Scale Challenge. And this we released 3 data sets that were then part of the 2021 KDD Cup. This KDD Cup also received a lot of attention and very positive response from the community. We had over 500 different teams register for to participate. 140 of them actually submitted some submission. They actually downloaded the data set, ran their code, and made a submission. And 120 of them actually submitted the final test submission and participated in the competition. As I said, we released 3 data sets. So we have 3 winners per data set, so 9 winners total, or we have 3 places, top 3 in each of the 3 data sets. In terms of participation, about half of the participation comes from China, a quarter from United States, and then the rest from the rest of the world. So basically Asia, excluding China, Europe and the rest of the world. In terms of teams coming from different institutions, about 60% comes from academia and about 40% comes from industry, which is also a very nice balance. For the 3 different data sets we released a node classification, node level prediction data set, a link level prediction data set, and an entire graph level prediction data set. And we see that the interest across these 3 different tasks was quite even. So about 150 to 180 teams registered for each of the data sets. And at the end, the node level and graph level received about 50 submissions, and the link level, the link prediction, received 30 submissions. In terms of data sets that we released, these data sets are orders of magnitude larger than what exists today. So the node level data set has 240 million nodes and 1.7 billion edges. The link level data set comes from Wikipedia. It's 90 million nodes and 500 million edges. And then the graph classification data set is a set of molecules. It is about 3.8 million different molecules, in total having 55 million edges. And each of these data sets is actually a real-world data set from a given domain with a real-world prediction task behind them. What I want to do next is quickly go over the 3 data sets and just give a bit of a sense of how the performance was improving over time. So the node level classification data set comes from Microsoft Academic Graph, and this is a heterogeneous graph of capturing academia. So we have nodes, institutions, authors, papers, citations between them. And the goal of this node classification task was to predict a subject area of the paper situated in this heterogeneous graph of, as I said, institutions, authors, papers, and then affiliations, authorships, and citations between the papers. Here, for example, when we released the benchmark, we used the existing architectures, and our best performance was about here. So let's say about 70% accuracy. This shows a rank of submissions versus accuracy. Higher is better. So, you know, what, let's say, state of the art at the time of the release of the competition was about 70%. Now the winners were at over 75, so 76, 77. So significant performance improvements have been achieved on this challenging data set. For a link level prediction task, this is a knowledge graph from Wikipedia. This basically takes the entire wiki data and represented as a knowledge graph. So basically these are real world entities and relationships between them. And the task is to do knowledge graph completion or link prediction, where for a given entity, we want to predict a missing relation for it. So it's a very challenging task. Here, for example, our best baseline back in February was about 85, and the winners were able to push this to 98 percent MRR. So this is a mean reciprocal rank of predicting the correct link. Again, higher is better. You see the significant amount of progress that's been achieved. And then the last is the graph level classification task. This is for molecular graphs, where the task is to predict an important property of a molecule. This is an important property for quantum chemistry. It's called HUMO-LUMO gap of a given molecule. And the way this is done today is that it's a expensive quantum simulation is being run for each molecule. This simulation takes hours to compute, and it's done on supercomputers. And the idea is that we can build machine learning models that can take the molecule and very quickly, basically instantaneously predict or output that same value that otherwise takes hours to compute. Here, the the metric is mean average error. The lower is better. And again, here, for example, the best baseline we were able to achieve before releasing the benchmark was about 15% error. The winners achieved about 12%. So again, quite significant drop, about, let's say, 20% drop in error achieved in this very short time. So the point being, the community put a serious effort into these data sets, achieved significant progress. We are today going to learn about what did the community do, what were the solutions coming up with the winning teams, and we are also going to summarize the approaches that other teams have taken. And we are going to leave and continue these benchmarks to be accessible so that further progress can be made. So the outline, the schedule for today is that we have 2 sessions. The first session today, the first part of the schedule will be about winners presenting their solutions. We are also going to present more details about each data set. And we are also going to present, kind of summarize the approaches and important innovations best submissions have made in order to achieve such a great improvement on all 3 different data sets. So this is what is happening for the first part of the workshop. And then in the second part of the workshop at 11 p.m. Singapore time, we are going to have a special session with invited speakers, keynotes, as well as a panel about benchmarks for graph machine learning. So for invited keynotes, we have 3 exciting speakers. Victor Prasanna from University of Southern California on scaling up graph neural networks. Marinka Žitnik from Harvard University discussing applications of graph neural networks to biomedical data science, and about new exciting benchmarks that are being developed in those areas, like the therapeutics data commons. And then Larry Žitnik from Facebook AI Research. He will talk about large-scale benchmarks in chemistry. And then for the panel discussion, we have 4 very exciting panelists: Yizhu Sun, Zheng Zheng, Shuiweng Ji, and Jian Tang, who will participate at the panel to discuss the future development of benchmarks and how to help the graph machine learning community move forward and achieve more progress. So with this, I'm done with my opening remarks. I'm excited for everyone attending the workshop, and we will now move to the next steps on the agenda.
Okay, so thanks for the introduction. And we now start with the winner presentations on the node level track. So my name is Matthias Fey. I'm one of the organizers of this KDD Cup. And I will first give a brief introduction to the data set and the task before each winner presents its solution in a 10-minute presentation. And after that, we will have a 15-minute Q&A session with all the speakers. So the goal of the node level track is to predict the primary subject area of archive papers in a massive heterogeneous academic graph. And so this task is of real practical uses because the volume of scientific publications has been increasing exponentially over the years. And what that means is that we can make use of machine learning models in order to reduce the burden of manual labeling for authors of archive papers, as well as for archive moderators. And furthermore, we can use such models that were developed to classify the vast number of non-archive papers which aren't yet labeled. So for dataset creation, we downloaded the complete set of 121 million academic papers in English version from the Microsoft Academic Graph. And those academic papers also come with 122 million authors that are affiliated to 26,000 institutions. And for dataset splitting, we split the data according to time, which models a realistic splitting scenario in which we want to label newly submitted papers to archive based on previous submissions to archive. And in particular, we want to train our models on papers published until the year 2018, use the 2019 papers to validate the performance of the machine learning model, and then use the papers in 2020 for testing the final performance. And those papers in 2020 were actually hidden to the user so that they can only make use of the validation set to validate model performance. And overall, this data creates a massive heterogeneous graph in which we have about 240 million nodes across 3 different node types. And those node types are paper nodes, author nodes, and institution nodes. And then we have edges connecting nodes between different edge types. And overall, we have about like 1.7 billion edges across these node types and edge types. And for edge types, we, for example, have relations that connect paper to paper nodes, where the meaning is that a paper cites another paper. We have author to paper nodes, meaning that an author writes a specific paper. And we have author to institution edges, meaning that an author is affiliated with a specific institution. And this sheer amount of data alone is quite challenging to handle, and in fact is by far the largest graph node level data set out there. And in particular, it requires efficient sampling strategies to train sophisticated GNN models. And furthermore, each paper node comes with a rich feature representation. And in order to obtain the features for paper nodes, we use a Roberta sentence encoder that embeds paper titles and abstract into a 7,168 dimensional feature vector. And so for storing this big feature matrix alone, this will require about like 180 gigabyte storage, even saved in half precision. And since we have a lot of random accesses on this feature matrix during training, we also require efficient strategies to not let the I/O become a major bottleneck in our training procedure. So we performed an initial benchmark analysis using different models. And in particular, we benchmark homogeneous models that purely operate on the homogeneous paper-to-paper graph. And we also benchmark heterogeneous models that take the full heterogeneous information into account. And in particular, we benchmark graph agnostic MLPs. We use a label propagation algorithm. We benchmark some simpler variants of graph neural networks that decouple predictions from propagations, namely SGC, assign, and the correct and smooth algorithm. And we also make use of GNN models that perform neighborhood sampling using GraphSage or graph attention networks. And for heterogeneous models, we convert our GNN models into heterogeneous variants in which we learn distinct weights for each individual edge type. And in our analysis, we can see that GNNs typically outperform more simple models, which can be, in my opinion, contributed through the large amount of data that is available to us. And we can further see that heterogeneous information is crucial on this data set to obtain good performance. So, for example, our best homogeneous model achieves a final test performance of 66.80% accuracy, while our best heterogeneous one achieves the final test performance of 69.42. But in fact, this performance was heavily increased by the winning solutions. And the winners of our competition on the node level track are the BD-PGL team from Baidu, the academic team from DeepMind, and in third place, we have the Synerise AI team from Synerise and Warsaw University. We also have some runner-ups that perform close to the winning solutions. And for runner-up teams, we have the Topology MAG team from OPPO Research. We have the Passages team from Nanjing and Beijing University. And we have the Deeper and deeper, bigger, better team from KAUST and Intel. And so as this figure shows, the competition led to major improvement on this data set compared to our initial benchmark analysis. And overall, the best solution achieved performance improvements that was 6 percentage points better than our best performing baseline, and which is really impressive in my opinion, given the tight time that the winning solutions had to come up with their solutions. And so with this, we are ready to jump into the 10 minutes talks for each team. And after that, we will have a 15 minutes Q&A session with all the winning speakers. And if you have any questions, please write them down in the chat, and we will try our best to ask those questions in the panel discussion. So now let's start with the first presentation, which comes from the first winner team, the BD-PGL team from Baidu. Thank you. Does everything work for you?
Hi, everyone.
Perfect. Hi.
Okay. Oh my God.
Are you okay?
Oh. Okay.
Yeah.
Everyone can see the PPT right now?
Yes.
Okay. Hello, everyone. I'm Shiyun Shen. We are the PGL team from Baidu Company. Today it's my pleasure to introduce our solution for the OGB large-scale node classification task in this KDD Cup 2021. Our report is divided into the following three parts: the background of OGB-LSC node classification dataset, and the solution we propose, including model modification and the trick we use in this task, and the experience result. First, since the OGB team have introduced the detail of the dataset, we will make a quick start introduced in this part. The dataset of OGB-LSC node classification MAC 214M is a heterogeneous academic graph extracted from the Microsoft Academic Graph. Given the archive paper situated in this heterogeneous graph, the competition aims to predict their topic. More specifically, in this graph dataset, there are three columns of node type, paper, author, and institution, totally add up 240 million. And there are three columns of edge relationship between the nodes, paper side paper, author write paper. Author is belong to institution. We split the dataset by time using all the data before 2018 to train model, 2019 to eval, and 2020 to test. Our model need to find the target subject area for paper nodes within 100 fighting street class, and we use ACC to estimate our model. Recent advanced approach for node classification are mainly based on graph neural network. OGB-based light provide early investigation on several classification methods, including GCN, GAT, RGCN, RGAT. We simply follow the best baseline model, RGAT, from them, and use our PGL framework to re-implement it. Moreover, our implementation can apply multi-GPU training and inference, which will speed up our further study. Following the baseline, our main solution named RUNMP is to make some modification based on the feature of this data to further improve the result. Within this data include these two features, large-scale semi-supervised and heterogeneous. For large-scale semi-supervised feature, we propose to unify the node feature and label propagation within a message passing model for fully utilized neighborhood information. For heterogeneous feature, the baseline model use different GAT to encode nodes with different type and get obvious improvement. We perform more kinds of relation-wise modeling in both sampling and model structure to get a better result. Compare with the traditional neural network, for semi-supervised graph data, GNN can incorporate neighborhood information to further improve result. However, right now, the GNN model only consider incorporate neighborhood node feature information and use the node label to supervise training their model. We adopt the idea from paper UNMP proposed to incorporate node feature and label as input in both training and inference to further utilize neighborhood information. We further adapt the masking label prediction strategy from UNMP to train our model for prevent the label leakage problem, since we use the label as input. Moreover, we find that adding random paper label during training can make our model more robust in prediction. For heterogeneous feature based on RGAT, we perform more relation-wise modeling. We perform relation-wise sampling with different amounts of sampling neighbor for each relations, where the baseline RGAT only take on neighbors as a homogeneous graph during neighborhood sampling, which cannot guarantee that each relation have at least one neighbor. Second, we change and place the bench non-layer just before neighborhood aggregation for each relationship, and we prevent parameter sharing for bench non-layer between different relationships, since different relationships should have their own domain scalar model. And we also design a weighted attention sub-layer for relation-wise feature aggregation, since different relation features should have different impact for final prediction. After introducing our RUNMP modeling, we also want to present some tricks we used in this competition. The original RUNMP only used the text feature as no feature as the baseline use. In this work, we want to find out the relationship between paper published time and prediction result for this citation graph. So as table, we simply perform the voting strategy on validation node by their neighborhood according their published time, and results show that the paper with more closer published time have a closer relationship, which indicates that published time can be a feature to guide the information aggregate for those nodes with same label. Therefore, we just use it as an extended node feature and use the transformer position function to encode it into the dense feature. And we can find that in the OGB method, the random walk-based graph structure embedding is often used as an extended node feature to further improve GNN model. Therefore, we also want to apply it into this large-scale competition heterogeneous graph data. We use classical representation method to encode this heterogeneous graph, and we adopt the implementation from PGL framework, which can be distributed training and inference the M2V embedding in such large-scale data. So finally, our RUNT model use 4 kinds of feature as input, including no test feature, no published time feature, and no graph structure feature, and partial no label feature. After training our model and making prediction, there is still a useful trick for further improvement. Paper APPNP find that simple post label propagate for those GN model can improve their predict result. In our work, we find that after using our RUNP model, which have been incorporated the label propagation in the model, simple post label propagate can have a little impact on the prediction. However, we find that if we perform the post label propagate on the filtering graph with a higher homophily ratio, we can achieve better improvement. Therefore, we perform a voltage strategy on validation node based on different filtering graphs, as table show. We find that simply voting on the co-author graph can achieve a higher prediction accuracy. And we use it as the final filtering graph, and we use the standard APPNP equation to perform the label propagation smoothing. In the experience, we first propose the result on the official training and validation data. Taking the RJT as baseline, we modificate it into RUNP and use 4 kinds of embedding as input. We can bring the performance from 70% to 73.6% ACC, absolutely 3.6 improvement for single model. Finally, use the post-label propagation smoothing. We can improve 0.05% ACC. We also add the validation data in training for get a better result like other team. In this experiment, we divide the validation into 5 folds, add the 4 fold into chain and the rest to eval. And we use the different N2V embedding and different config to train our state model. Finally, we ensemble all the model up and get a 77.773 ACC eval result, which probably improve 4 points ACC compared with previous single model. We submit its test prediction as final result and get 75 and 75.49% ACC in test set and win the first place in the final competition. That's all. And more detail about our solution can be found in our code and report. Feel free to check the improvement from the related link. Thank you. Thank you, everyone.
Thank you very much. We now continue with the second place, the academic team from DeepMind.
Hello. I am sharing the screen. Yes, I hope that's visible.
Yes, it is. Thank you.
Okay, great. Perfect. Yeah, thanks a lot. My name is Shantanu, and today it's my pleasure to be presenting our work in the OGB Large Scale Challenge on the MAG dataset. And this is work done on behalf of these amazing collaborators. So Ravichandra, Peter, David, Andrea, Jonathan, Thomas, Alvaro, Jacqueline, myself, and Peter. First, I'd really like to thank the organizers for creating such an interesting and impactful challenge. I think This was really like a public data set at really unprecedented scale. And it was nice that it also had a lot of real world relevance. And I like one of these quotes from the website, one of the goals of the data set was to encourage and really inspire more large scale GraphML research. And definitely on our side, it inspired a lot of efforts into like engineering, data analysis, and a lot of interesting research questions. So yeah, we really had to push on all fronts to get good results in this. Okay. I think one of the biggest and most obvious challenges of large scale GraphML is on the engineering side. And there's a lot to say about this. But one thing I'd really like to highlight is that our entire engineering pipeline was built on the JAX ecosystem, as opposed to using the baseline PyTorch code that was provided as baselines. And the nice thing about this is that it really forced us to make rapid progress in development in a lot of utilities for large scale GraphML. So things like batching utilities or neighborhood subsamplings, things like that. And all of this has now been open sourced with our submission. So anyone in the community can really start using JAX to do their graph research. Okay. Then getting down to the feature engineering. One of the things we first noticed was that the 768 dimensional BERT embeddings are probably too big. So we tried projecting it down to 129 PCA dimensions using PCA. And this gave almost the same results, but most importantly, it improved our iteration speed and allowed scaling to much larger models to get better performance. We get the features for the author and institution similar to the baseline, just taking averages. We also make use of the paper year by discretizing it into 20 buckets and also adding the bitwise representation. And finally, we also add the label, like the true label of a node to its features if it's known. So for example, if we're predicting the label for a certain node and there are some other papers in its neighborhood and we know their true feature, true label is part of the feature. And as we can see, this improves performance quite a bit. Another thing we noticed looking more deeply into the data is that there are many duplicate nodes in this data set. And that could be because a paper has maybe an archive version, but also multiple conference versions, maybe a workshop presentation and so on. And we can identify these duplicates since they have the same title and abstract usually, which is what the BERT embeddings were computed from. And interestingly, 10% of archive nodes have at least one duplicate, meaning that this impacts the data we're interested in a lot. So we simply merge these together. So we merge the labels, their out edges, which is not super interesting, but also their in edges, which is it makes quite a big difference. Because usually, whenever you're citing something, you try to cite the official confidence version rather than the archive version. So the version of the duplicate, which we're actually interested in predicting, often had fewer incoming edges than the other duplicates. So merging these gives us much more informative neighborhoods. Coming to the neighborhood sampling strategy, instead of sampling with replacement per layer, we made a couple of changes. First, we sample a different number of neighbors per type, so maybe more papers than authors. We also sample without replacement and merge the nodes in the tree to form a DAG. So for example, if there's some paper P1 written by authors A1 and A2, and it's being cited by a paper P3, but A1 and A2 have also written P3, then with the old strategy, you would have something like this on the left, where P3 is duplicated 3 times. But after merging, we get a much more natural DAG representation like this. Another change we made is taking advantage of the paper year during the sampling. So if we're sampling a neighborhood for a central paper P, we ignore any paper which is newer than P. And the reason for this is to reduce some of the train test distribution split. Because we noticed that papers before 2018, which we are training on, have been cited by newer papers, but the papers we're testing on in 2020 have not yet had a chance to be cited. So both of these changes actually make our neighborhoods smaller, right? Because we're reducing duplicates and ignoring newer papers, but they also make them richer because they're more informative for the same sampling budget. Therefore, this allows us to increase the budget and get larger, more informative neighborhoods. And we can see that this also makes quite a big difference. In terms of model architectures, rather than using the heterogeneous GAT models, we use homogeneous NPNNs. And this is nice because they're theoretically more expressive, but also because they're homogeneous, they practically had much fewer parameters, making scaling easier. And in the end, we used a bidirectional MPNN with 4 message passing steps. And we saw diminishing returns by increasing the message passing steps. So we kept it as 4. And one of the most interesting things we were looking at the end was how really to use the unlabeled data in the graph. So we know that 1% of the papers are archive nodes, which have labels. So that's great. But what's the best way to use the other 99%? For this, we explored using bootstrapped graph latents, or BGRL, for self-supervised node representations. So now each batch would have a mix of labeled nodes for the supervised loss and unlabeled nodes just to shape the representation. We don't have time to go into the details of how BGRL exactly works, but it's up on archive, and this is just a quick sort of skeleton of what the objective looks like, but it basically works by bootstrapping representations from each node. So as a first step, we explored applying this on top of the labeled nodes only, so just as an auxiliary loss. So even when we're not mixing unlabeled data, but just using it to shape representations, we see a large increase in performance between the fully supervised and also using BGRL to shape the representation. And it's also slightly better than another method called Grace. Next, we add more and more unlabeled data. So now each batch would have a ratio of some amount of labeled data and some amount of unlabeled data. And we vary this from 0, which is the baseline, so only labeled data, to 1x, 5x, and 10x the unlabeled data. And we see this very nice monotonic increase in performance the more unlabeled data that we add. And just because of the time constraints of the competition, we stopped at a ratio of 10. But it could have continued maybe up till 99 to reflect the true balance of the data in the graph. And finally, since mixing more unlabeled data is preventing overfitting, we just run for 10 times longer. So we could train for up to 500,000 steps without overfitting. And again, because of time constraints, we just stopped here, but it's really improved performance. Finally, so just some tricks to boost our final performance. We know that these new sampling strategies increase our neighborhood size, but we still can't fit the entire neighborhood. So for our final predictions, we averaged our model predictions over multiple independent samples of the neighborhood for each node. And we can see that this does give a slight boost. And again, we also train on the validation test set as well for a final submission. So we split it into 10 parts, train 10 models, each on the training set plus 90% of the validation, and use the other 10% for early stopping. And at the end, ensemble across these 10 models for the final predictions. And this gave around a 2% gain in our internal validation testing. So just as a summary, I think it was a really nice data set and challenge. We learned that there are a lot of very non-trivial engineering challenges to really scale these methods up. We really got the sense that a lot of methods that work well for very small graphs either can't or don't scale to much larger graphs. And for maximum performance, we really need to understand the data we're working with, like finding these duplicates and so on. And finally, unsupervised learning can give a lot of gains when we have a lot of unlabeled data. So thanks a lot. Our paper has many more details on this, and the code is online. Thank you.
Thank you very much for this great talk. And we continue with the third place with Sunrise AI team.
Hi, good morning, everyone. I will share my screen. Okay, good morning, everyone. My name is Michał Daniluk. I am a research scientist at Sunrise, and today I will present our third place solution to KDD Cup Challenge node level track. So, to remind, the goal of the challenge is to predict the primary subject areas of a given archive papers, which is cast as an ordinary multi-class classification problem among 153 classes. The evaluation metric is the classification accuracy. And we tackle the task with an efficient model based on our previously introduced algorithms, MD and Cleora, on top of the simplistic feed-forward neural network. We use MD to represent nodes in the form of sketches, which are histogram-like structures that represent density on multidimensional manifolds using locative-sensitive hashing. For example, you can represent all cited papers as a fixed size structure, which we called sketch. And the second method which we used is Cleora for label propagation. And the model architecture itself is very simple. It is a 4-layer residual feed-forward neural network with leaky ReLU activations and batch normalization, and with 153 outputs representing the possible archive classes. The most elaborate part of our solution are the input features, which are pre-computed and fed as a model input in the form of a large concatenated vector. First of all, we represent cited papers as a sketch using MD. And remember that sketch can represent variable size of nodes into fixed size histogram. I will explain this in more detail in the following slides. Similarly, we apply MD to represent papers which cited the given paper, papers of given paper authors, and institutions of a paper. Secondly, we use label representation of neighbors, basically looking at the labels of cited papers, citing papers, and other papers of the same authors. We use also bird paper representation as an input to the model. Furthermore, we apply Cleora, our open source method, to represent a given paper and its neighbors. I will also tell you about it more in the next slides. And in addition, we also include some simple numerical features such as the year of the paper, number of authors, number of cited papers, and so on. Okay, let's dive into our first part of the model, which we called MD. We published a paper about it, so I encourage you to read it. This method was also used by us with success in Booking.com Data Challenge and Twitter Rex's Challenge competitions. It's also used in our production environment to provide recommendations. It is inspired by local sensitive hashing algorithm, and the most important part is that MD creates sketches which can be seen as a compressed representation of variable size vector representation. An example of full MD algorithm run is presented in this picture. So in next slides, I will go step by step through it. So first of all, MD operates on upstream representation vectors. In our case, these are bird embeddings of cited papers. So in this picture, for example, our given paper cites 3 papers. Each of them is represented by a vector computed by bird. And the idea is simple. We divide the item embedding space into regions and assigning items to specific buckets based on similarity of their embedding vectors. So in this picture, the red dots denote the embedding of a specific paper. The embeddings are partitioned with a data-dependent locality-sensitive hashing algorithm. And the purpose of manifold partitionings follows the logic of locality-sensitive hashing. So similar data points should be mapped to the same region. After that, we assign each cited paper to a specific bucket. For example, the first and the second papers are assigned to the 0 bucket, and the third node embedding is assigned to the third bucket on this picture. And each partitioning is done with k hyperplanes, and it is repeated n independent times. The region IDs of each input publication are stored in matrices M, which are then binarized to obtain matrices B, which form the sketches of individual papers. So to sum up, each paper is represented as one hot encoded vector, which we called sketch. And the sketches of individual papers are aggregated with simple summation to obtain a sketch of all cited papers. So we can think about it as a histogram-like vector representation of neighbor papers. So it allows to compress a variable length sequence of publications into simple 1D vector of constant size. Okay, that's it about MD. And the next input to our model is label representation of neighbors. So it's very simple. For each neighbor node with labels, and one hot encoded label vector is created. And all such vectors of all adjacent papers are summed and L2 normalized. So this results in 100 a 53 vector representation. We consider 3 types of nodes as neighbors: cited papers, citing papers, and other papers of the same authors. So for each type, we have separate vector. We also used Cleora, a fast and efficient graph embedding technique. It is open source method written in Rust. Cleora combines intuitions from both random walk-based methods as well as graph convolution networks into a simple solution. So instead of sampling individual random walks, we consider all possible random walk transitions in a Markov transition matrix. And multiplication of vertex embedding by this matrix allows to perform all possible random walks in parallel with one large step. So it relies on multiple iterations of normalized weighted averaging of each node's neighbor embedding, followed by normalization across dimension. And here, I present a simple example of Cleora. We have a graph with 6 nodes. And first of all, we create a sparse Markov transition matrix. For example, we can see that from node 1, we can go to node 2 or node 5 with the same probability. And matrix T consists of embeddings for each node, which is randomly initialized at the beginning. And the output embedding matrix is just multiplication of Markov transition matrix and matrix T, followed by normalization across dimensions. That's it. All it does is iterative neighborhood smoothing and renormalization. And apparently that's enough for high quality vertex embeddings. And here we have 2 parameters, D, which is the size of the embedding, and number of iterations, I. And I will present here a simple visualization of applying Cleora in our scenario. Here is a small sample of our graph. Let's say that edges represents citations and nodes represents papers that belong to one of the archive classes. So first of all, we randomly mask 50% of nodes. You can see that unmasked nodes have red outline and the associated labels are presented. And embedding computations proceeds exactly as in Cleora, with the exception of node embedding initialization. Concretely, the unmasked papers which do have assigned labels are initialized with one whole encoded vector expressing the labels instead of random initialization. Masked and non-labeled nodes have the embedding initialized to all 0 vectors. And then we apply a first iteration of Cleora, which results in new embedding for each node. And it is the average of each node's neighbor embeddings, followed by normalization across dimensions. For example, the green node was masked and initialized as all 0 vector, and after first iteration, it represents the L2 normalized average of all neighbors from previous iteration. So you can apply as many iterations of Cleora as you want. In this competition, we apply 2 iterations. So first iteration of Cleora used vector representation from one hop vector's neighbors, and the second iteration used also vectors from the second hop away in the graph. And Cleora training is done using unmasked label nodes in the training set, and the masked nodes are used for full model training with its labels used as output. So it allows us to provide efficient ensembles. Each of them was trained on different half of nodes. And we also include the simple features expressed with a single number, which are the number of cited papers, the number of papers which cite the given paper, the number of another papers of the authors, the number of authors, and publication year, which was quite important. And the model architecture, the model is written in PyTorch. We train it on single Azure instance with using one GPU, and training a single model takes around 21 minutes per epoch, and inference is very fast. It takes around 7 minutes for all testing nodes. And our model was trained only for 2 epochs. In addition, we observed the performance gains after sorting the data set according to date. So we apply this in our final submission. And to achieve maximal performance, we train 60 independent ensemble models. And our final score of the accuracy metrics on the hidden set is 74.6%. And that's it from my side. Thank you very much.
Thank you. Okay, so yeah, thanks to all speakers for their awesome solutions and presentation. And before the Q&A session starts, which you can now do and ask some questions to the speakers in the chat, we first try to give a brief summary regarding common trends among the winning solutions and runner-ups. And so this is mostly a GNN focus. So I'm interested to hear more about the synergized AI approach and how it differs from graph neural networks. But so the first trend we identified is usage of relational-wise neighbor sampling in GNN models. And in particular, what that means is that we want to sample neighbors for each edge type individually. And overall, this ensures that each relation has a meaningful neighborhood and that each edge type is also present in the sampled heterogeneous graph. And furthermore, we see that the amount of neighbors sampled for each relation should approximately correspond to the original neighborhood distribution. And for example, in the Microsoft academic graph, there exists more paper cites paper relations than author writes paper relation. And so it's natural to sample more paper neighbors than author neighbors as well. The second trend we identified is the usage of labels as inputs, which is also called masked label prediction. And we also see this trend being applied to other node level OGB datasets as well. And what that means here is that we combine label propagation and feature propagation into a single model. And we see that this can boost performance quite heavily, even in large-scale graphs, where we would expect that the huge amount of data is already sufficient to predict the given label. And one important step here is that we need to mask out the labels of training nodes in the mini batch to ensure that there is no data leakage. So other trends that we identified is the modification or enhancement of the initial feature matrix. So for example, we see solutions that combine method path to vec embeddings to the feature matrix. We see solutions that enhance the feature matrix by simplified graph convolution features. We also see trends that just put the node type IDs to the feature matrix as well. We see solutions that add random features to the feature matrix, but we also see solutions that reduce the dimensionality of features using PCA and stuff like that. So other trends that we identified is usage of post-processing on the final predictions. For example, we see solutions that further smooth the final predictions using the correct and smooth algorithm. And we see solutions that retrain models on the validation set. And we see solutions that make heavy use of ensembling. So with this, let's start the Q&A session and welcome our speakers once again. And if you have any questions, please feel free to ask them in the chat. To start the discussion, I will first ask a question targeted to all the speakers. And what I would like to know is, sorry, I didn't actually start the video. But what I would like to know is from each of you, like what is the most challenging aspect when working with such a large scale data set, in particular in comparison to working on smaller data sets that were typically used in benchmarking graph-based machine learning models. So who wants to start? We can go in the order of winning solutions, maybe. Yunchen, can you hear me?
Yeah.
So my question was like, what was the most challenging aspect of this competition in your opinion?
You mean what kinds of challenges I mean in this competition?
Yeah.
Since we are the team by the company, we need to use the pedal framework, another deep learning framework using in China. And so we need to do the competition and write the code from scale up. And we need to imply the baseline from start. So we need to do this thing. We need to more time to do this thing. To do this thing. So it may be my change to use our framework to re-imply and get the same result like the PYG, your baseline.
I see.
Thank you.
Other opinions?
And after imply our baseline, we will have more time. We will have time to do the study, and we would like to make the study from data driving. Is our opinion to make the modification for our model for this competition from data driving. Yeah. Thank you.
Thanks. Shantanu from DeepMind,
Yeah.
What is your opinion?
Yeah, I probably very similar to what Jincheng just said. I think we also implemented the whole thing in JAX. And so I'd say what is the one big challenge is definitely on the engineering side, especially getting things to work efficiently, up to the point that you actually put things on GPU, right? Like very efficient node sampling or getting the neighborhoods, things like that. Even as you said, getting the entire feature matrix in memory. I think one of the reasons that we did PCA was so that we don't need to have so much RAM around. So yeah, I think definitely those are part of the challenges. A good thing came out of it is that we actually did write the code and now it's all open sourced. But yeah, I'd say the engineering aspect is definitely one of the overlooked aspects of scaling these models up.
Yeah, so there's one follow-up question on this one, and it is given the graph is so big, how difficult is it to perform PCA on the graph?
Yeah, that's a really good question. I saw it on the chat. Yeah, I think what we did is we could actually do PCA on the entire 360 GB or 180 GB thing. So we did random samples of 10,000 papers and just computed the components based on that. And we did it for, I think, 3 or 4 random selections, and mostly things didn't change too much. So we're like, okay, the 10,000 is a pretty decent number. But yeah, I mean, that in itself is a huge challenge of working at this scale. Yeah.
Thank you.
Okay, I think that for us, the biggest challenges are a couple of them. First of all, we doesn't have a lot of computation resources, so we need to have a very efficient model which train fast and the inference time is fast. And furthermore, we also doesn't have a lot of time for that challenges because it's not our primary task. And in addition, in the same time, we also took part in the Rex's challenge, so we needed to split our resources to both challenges. And yeah, and that's it, I think.
Okay, thank you.
Yeah, sorry, maybe yeah, maybe we should close. But I have very quick question that I'm very curious to all the speakers. maybe very quick question, quick answer is fine. But is there any method that suddenly start to work on large scale data that you didn't see to work on smaller scale data? Is there any finding on that aspect? If there is any, yeah. or did you find those method that's developed for OGB, for example, medium scale data set just works fine on this large scale data set? Or is there any new thing that suddenly start to work or suddenly didn't work? Any thoughts? Yeah, go ahead.
Yeah, one thing is definitely like using BGRL for unsupervised learning. So before this, we were actually like when we were developing the method, we were working with much smaller scale graphs where the entire graph was actually fitting in memory. So we worked with like the OGBN archive dataset, which is I think like the smallest one. And over there, like it was hard to actually get a substantial improvement. Possibly because all the nodes that were there, you were already applying a supervised loss to. So like that's very different where you have like 1% labeled nodes and 99% like this vast amount of unlabeled data. So I think that was one of the things that really unlocked the potential of just methods that are better able to use scale, benefit from scale. Like let's put it that way.
That makes
and
sense.
I think it was like, it was also, I think for me, a very surprising thing that it did get such a big improvement and delay overfitting for like 500,000 steps as opposed to like 50,000 steps without it. Yeah, I think it was a very powerful method. Yeah.
Thank you. Any other thoughts?
Yeah,
Maybe we are running. Yeah, go ahead. Go ahead.
Also tell you that in our production environment we also have similar graphs. I mean similar sizes, and I think that there are a lot of challenges, as we said before, and applying. I think we should focus on applying the efficient methods. And for example, our model, we train it only for 2 epochs, and after that it overfits. So I think if we have even more bigger data set, it should work just better. So yeah, that's it from my side. Thanks.
Thank you. Thank you.
So I have one last question to all of you, given that we're running out of time, sadly. But yeah, given that you had more time for this competition, is there anything that you would like to also have experimented with, or is there anything that you would like to add to your model? Any thoughts on that? Yeah, go ahead.
Maybe, can I answer this question or just
Yes,
later?
you
Yes,
can.
Okay. Since we just changed the model with 2 layers in this competition, and before because the GPU memory limitation, we just changed the model with 2 layers, and if give me one time, we will try to find out the way to train a model with deeper and wise. Since in image or NLP tasks, we can find that the model deeper, the result better they can get. And we also want to find the way to get a deeper GN or wider GN to get a better result. That's it.
Thank you. Other opinions?
Yeah, I think for us, we did, I'm sure like heterogeneous models carefully tuned would have ended up boosting performance. We did experiment a bit at the start, but by the end we were just rushing with the deadlines or like, whatever we have, let's just go with that. So that, and also on like the data side, we were exploring for some time, trying to add new edges which don't already exist in the data set. So maybe like based on similarity of BERT embeddings or something. So trying to do something like, this paper really should have cited this paper, but they didn't, something like that, just to get even more informative neighborhoods. Yeah, that's something that maybe could have improved performance a lot, but we didn't get sufficient time to explore that. But yeah, maybe that's a promising direction.
Yeah, sounds great. And we are looking forward to seeing further improvements on this data set based on your suggestions. Okay, so now we are running out of time and we continue with the link level track. So thanks again to all of the speakers and for the discussion. And yeah, thank you.
Okay, can you guys see my screen? Okay, so I will kick off the presentation and the discussion on link level track of the large scale challenge. I'm Hong Yuren, and for the link level track, we will have a similar structure as the node level track. Basically, I will first do an overview and introduction of the task and the data set, and then we will have the 3 winners presenting their exciting solutions. And we will also have a Q&A session afterwards. Yeah, so for the link level track, the goal or the task is really to predict the missing links or missing facts on a massive knowledge graph. So for these knowledge graphs, they are basically a form of these heterogeneous graphs where multiple types of entities and relations exist. And knowledge graphs can encode like many real world facts in such a triplet form. Okay, so for the real world large knowledge graphs, the challenge comes with it is really twofold. So one is that they are often very heterogeneous without schemas, or it requires like efforts to manually design schema. And the second is that they are often like incomplete with a whole bunch of missing facts, missing entities and missing relations and so on. So in OGB large scale challenge, we introduce a new wiki KG 90 million dataset, which are extracted from the entire Wikidata knowledge base. So it contains like this 504 million triples from 87 million real world entities and 1.3 thousand relations. Yeah, so there are like some several notable differences from existing KG datasets. Namely, we basically reuse the entire Wikidata to construct our KG, and the KG is comparable or even larger than most of the existing KG benchmarks. And also we have really designed these real world splits, right? In the sense that they come from 3 different timestamps. And lastly, we also provide the text features for all the entities and relations on the KG, which are basically, we use a Roberta representation of the short description of the entity or relation on the Wikidata. Yeah, so specifically, we picked these 3 timestamps in 2020 and use this to really create the training, validation, and test split and test edges. So for each validation test edge, right, we provide 1,000 negative entities, which are uniformly selected from the graph. And also we provide the only one ground truth tail node. And the goal is really to rank the ground truth node as high as possible among the 1,000 candidates. And for the evaluation metric, we basically use the mean reciprocal rank, which is commonly used in the literature. Yeah, and I also want to emphasize that there is some limitation since the negatives are like uniformly sampled from the graph. Then, for example, although a link is about a country, there may exist some like easy negatives, right, in the candidate set, like, I don't know, people or fruit, right, which can be easily filtered by the machine learning models. Okay, so for the baseline models, we really follow and use several conventional embedding-based methods. And the idea is that we can have an encoder that maps each entity and relation to the latent embedding space. And we can also design a decoder that scores a triplet using the entity and relation embeddings of the triplet. So for this encoder, we have 3 different design choices. The first is this shallow embedding, which basically means that we train an embedding matrix, and we can use embedding lookup to find the embedding of an entity or the relation. And the second is this Roberta embedding that directly uses the Roberta feature as an embedding for the entity and relation. And the third one is concatenation. Basically, we can combine the two using concatenation. And then for the decoder, we use the 4 methods, transy, dismount, complex, and rotate. And the distance functions are shown on the side. And all the 4 models are really prominent models, prominent like KG embedding models in the literature. And as this initial benchmark analysis, we find that combining the textual representation and the shallow embeddings actually perform the best, right? Where we can achieve like more than 10% performance improvement over only like learning a shallow embedding matrix or only using the Roberta features. Yeah, so we have 3 winners from Baidu and Harbin Institute of Technology and University of Science and Technology of China, respectively. And they all achieve like super high performance. And I would really like to congratulate them again. So here are the performance of the winner teams as shown on the slide, and also runner-up. And all teams achieve like more than 95% mean reciprocal rank, which is like very impressive. And yeah, and we also have the runner-up team, the team Little Ant from the Ant group. And here's the plot of the winners and our initial best baseline. They have basically improved the performance by more than 10%. Okay, so now I'm super excited to have the winners present their methods. And also for the audience that would like to raise questions, please feel free to send them in the chat. And later we will have a Q&A session and after the 3 presentations. I would like to first welcome Huijuan Wang from Baidu to present their top ranking method.
Okay, hello, can you hear me?
Yes, please go ahead.
Okay, wait a minute. I'm sorry, I have to leave for a moment, and then I can share my screen.
Shall we start from the second place winner? Yeah, maybe we can wait for 1 minute or 2. And then if they don't show up, we can play the second. Okay. Seems to take some time. Let me just play the second place winner. Okay, sure. And you can type in chat to tell them that we are playing. Yeah. Okay, so the second place winner, we have recorded talk. So let me share the screen and play.
Hello everyone, we are team Oh My God. Here I will show you our technology solution for this competition. Our work can be divided into 4 main parts. The first one is introduction, the second one is backbone, the third one is method, and the fourth is experiments. The last one is conclusion. First, I will introduce the details about this computation. The computation dataset is a knowledge graph extracted from the Wikidata knowledge base. The task is to automatically complete missing triplets that do not yet exist in the current KG, given the hand node, relation, and the tail node. The table 1 shows the basic information of the dataset, concluding entity number, relation number, and triplet number. Our team has chosen some classical link prediction methods. The table 2 shows the comparison of the modeling capabilities. Results on the valid dataset is gated by 200 denominations and 100 negative samples. Considering that the result is not satisfactory, so our method has made a lot of improvements. Our method consists of the following 3 aspects. The first one is the more powerful representation vector learning. The second is the complementarity between different models. And the last one is statistical analysis based on dataset. I will show the detail of the more powerful representation learning. Since the size of the model and the method of training can have a huge impact on the final performance, the experiments from multiple aspects are conducted to determine which type of method is more suitable for large-scale datasets. Especially, 1. Different representation denomination of entities ranging from 200 to 768. 2. Different number of negative samples ranging from 100 to 1000. 3. Different line of material perceptual ranging from 1 to 3. Then, I will show the detail of the complementarity between different models. The knowledge learning by different models can be different. Thus, multiple models can system with the experiment function, which can greatly improve the performance of the model system. Motivated by this common sense, we explored different performance of the dataset models and then tried to linearly combine these models into a system. The following methods are what we have explored. Models consist Chassis complex, Dismatter simple, Rota PRI, and Autosave. The loss functions consist of logistic, focal loss, and the model combinations we use the weighted search based on grid search. Finally, I will show the detail of the statistical analysis based on datasets. Step 1 for each relationship in the valid dataset or test set. Count the frequency of its candidate entities. Step 2. If the frequency is higher than 5, remain the entity and the related frequency. Step 3. Sort in reverse order by frequency. Step 4. Select the first 700 entities as candidates of positive samples. If the number of entities greater than 5 is less than 700, All are selected, noted as CAN. Step 5. For each relationship, intersect the 1001 entities in its quantities with the CAN set obtained in the step 4. If the size of the intersection is larger than 10, then all of the 10 entities will be sorted according to the frequency of its occurrence and the results of the reverse order as the prediction. If the size of the intersection is less than 10 but larger than 0, the remaining entities will be filled in according to the score predicted by the model. If the intersection is empty, the prediction score of the model is used directly for sorting. In this part, I will show the detail and the result of our experiments. Table 1 shows the impact of the different dimensions of entities on the learning results. The higher the dimensions, the better the prediction performance. Here we take Tracy as an example. And the table 2 shows the influence of the different negative samples on the learning results. The more negative samples, the prediction performance, the better the prediction performance. Here we take Tracy as an example. And the table 3 shows the influence of the different layers of material perception on the learning results. For conducted training methods, the best performance is obtained when the layer of material perception is 2. And the table 4 shows the model and the perimeters we finally submitted. We use the grid search to find the obtained weighted complementary model. After about 1,000 evaluations, we select the weighted should in table 5. And the table 6 shows the results on the final test side of the submitted model combination. In conclusion, in our solution, 3 process model representation learning, evaluation of the complementarity between each model, and the analysis of the dataset play a big role in the final result of the game. The third strategy is very tricky, and we are also very surprised by the existence of the big bias, because the evaluation set can be hacked without touching the test site at training. But when deploying the link prediction method in practice, the small candidate sets will not be given. We are honored to help the organizer fight such problems. Any comment can contact us anytime. That's all. Thank you.
Okay, then let's welcome Regina for the presentation.
Hello. 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 Can you see this PowerPoint?
Yes, yes, please go ahead.
Yes. Okay, let's begin. Sorry for the accident. Okay. Hello everyone. I'm Huijun Wang, coming from Baidu PGL team. It's my pleasure here to share our solution. The outline is as follows. First, I will briefly introduce the background and then detail our solution from 3 aspects: the framework we used, models, and features. The results and the conclusion are given in the last. Logic graphs are ubiquitous in our life. We can format them as triplets comprised of a hand, relation, and tail. To effectively make use of this data structure, representation learning methods are proposed to encode entities and relations as embeddings. However, as the scale of previous datasets is very small, the development of algorithms on large datasets is limited. Thus, this dataset is proposed. It is extracted from Wikidata and split by time steps at September, October, and November. It has 87 million entities and 1,000 relations. Each item is also provided with a text embedding coded by Robota. Especially, there are more than 500 million triplets for training. The embedding quality is evaluated on the link prediction task. Considering the scale of entities, only 1,000 candidates are randomly sampled to calculate MR metric. And we have to note that there are more than 200 gigabytes parameters. How to store and operate them is challenging. To deal with these problems, we developed the PGLK framework based on PaddlePaddle 2.0, which has the first industrial heterogeneous parameter server architecture. It can support super large-scale graph embedding. At the same time, CUDA streaming and pipeline parallelism technologies are adopted. It significantly improves computing efficiency by utilizing machine resources thoroughly. For the model part, we first consider simple and effective translational methods. The basic version is TransE, which assumes that relations are translation operations between entities. But this assumption cannot model symmetric and anti-symmetric relations. Translational models in higher domains are proposed, such as rotate, quanti, and OTE. But in our practice, we find that OTE cannot converge on this dataset. Let's look at its scale function. There is a scalar tensor to scale the outer norm of each group of embeddings. Its formula has an exponent operation here. This will enlarge values and could lead to this issue. Thus, we propose node with S3 normalization on the scalar tensor. This makes the training process more stable and gets a better result. Previous models all define training objects separately on each triplet, but the semantic meaning of a given entity is also influenced by its context. For example, given pedal here, you may associate it with the boat, but if more surrounding neighbors are given, such as framework or Python, we will figure out that it refers to Baidu's deep learning framework pedal. So we should also consider modeling this data structure. First, we randomly sampled entity sequences and then use skipgram to learn entity embeddings. But for two entities like Alice and Bob, there are multiple choices for their relationships, like friend and enemy, couple, and so on. So relations play a very important role here. We should also model relations in context. In this case, we use features of neighboring entities one hop away to embed the central entity. There are two kinds of neighbors: hand neighbors with central entity as tail, and tail neighbors take central entity as the hand. Without loss of generality, let's take TransE as an example here. It assumes that hand plus relation equals tail. Correspondingly, we define messages from the hand entities as hand plus relation and the messages from the tail neighbors as tail minus relation. And then the proposed relational post-smoothing method, the whole updation of it is as follows. Relational methods from neighbors are summed up as smoothed embeddings. Because the original and the embedding also can more training triplet information, we use a scalar factor to make a weighted aggregation. Such a process is summarized as the formula. This strategy has 3 advantages. First is non-parametric. There are no gradients or backward. And second, it is efficient and we can fastly iterate 20 times on WikiKG 90 million dataset with Hadoop. And third, it is effective. And we evaluated our proposed RPS methods on 2 benchmark datasets, and the experimental results in this table show that it can help triplet-based methods break away from local and optimal and get a better result. Okay, besides implicit embeddings learned by previous models, we can also find some patterns directly from knowledge graphs, like person graduated from school. Entities belong to person class will more probably be the hand of graduated from relation. We can calculate the probabilities of each pair arising together and directly predict new triplets according to these features. And specifically, we define the 7 hand-to-tail features to describe interactions between entities, and as well as 5 relation-to-tail features for the correlation between entities and relations. And this figure shows the overall procedure of our solution. On the one hand, we encode entities and relations into embeddings with the existing and our proposed methods. And on the other hand, we construct features directly from knowledge graphs. And finally, we use heuristic search to combine learned embeddings and features for the final prediction. And this table shows the experimental results of our solution on the validation dataset. And as we can see, we use 16 models and 12 features, which are constructed from both training triplets and validation candidates. And finally, we get 0.979 MRR result on this task. And our contribution can be summarized as follows. First, we develop an efficient and scalable PGRK package, which can support large-scale knowledge graph embedding. And second, we modify the OTE model into a robust version for large-scale knowledge graphs, named Node. And third, we propose the relation-based post-smoothing strategy, which can effectively spread multi-hop neighboring information without the external parameters. And the last, we achieve the SOTA performance on the WikiKG 90 million dataset. And for the future work in our experiments, we find that the embedding quality benefits most from proper modeling. And so we can spend more energy on this part in the future. And besides, we define the non-parametric RPS strategy for neighbor aggregation here, but how to apply the parametric graph neural networks on large-scale data sets, or on the other hand, how to fastly training these models is still worth exploring. Here are references in this PowerPoint, and thanks for your listening. If you are interested in our work, you can refer to these links for more details, and thanks again.
Okay, thank you, Huijian, for the nice talk. And finally, let's welcome Jianyu Cai from Team Graph Miracles.
Hello, can everyone hear me?
Yeah.
Okay, I now share the PowerPoint. Please wait for a minute. Oh, sorry, I just installed the Zoom, so it asks me for privilege to share my screen. So I need to log out and log in 1 minute later. Is that all right? I'm sorry.
Yeah, sure.
Okay.
No worries.
Okay, hello everyone. Can you see the screen here?
Yes, please go ahead.
Okay. Good afternoon, everyone. I'm Jianyu Cai from University of Science and
Sorry,
Technology.
we are seeing
Okay.
your presentation view.
Okay, I will.
Yeah, you may need to.
I will change it.
Yeah, maybe share your another monitor.
Yeah, thank you. Okay, can you still see the scripts?
Yeah.
You can still see the scripts. Okay, let me see. Okay, I'll just start the presentation without scripts. Hello, everyone. Good afternoon. I'm Jianyu Cai. I'm from University of Science and Technology of China. My team members, including me, Jiajun Chen, Tao Xingpan, Zhanqiu Zhang, and my tutor, Professor Jie Wang. I would like to thank the organizers for organizing such an exciting competition and the audience being here for listening our presentation. My presentation including 4 parts. First, I'll introduce our method. First, I will introduce the overall architecture and then introduce our several sub-modules. Overall, our model consists of 3 parts, including a rule miner model and a knowledge distillation sub-module. Briefly, when we have this knowledge graph as input, we first apply the rule miner to mine rules, and we then use the generated rules to generate high confidence new triplets to add them in the original knowledge graph, and then use the knowledge graph to train our model. Our model takes head entities, relations, and candidate tail entities as inputs, and it outputs the scores of the candidate tail entities. The knowledge distillation module takes the output of the candidates as input, and then it distills the ensemble models, knowledge of the ensemble models into into new single models. I will repeat this process for several iterations to allow our model to learn new knowledge from the previous ones. First, the rule mining. We use AMIE3 as the rule miner. Since the knowledge graph is too large, so we split the knowledge graph into 5 parts and apply the rule miner on each part respectively. We then generate rules based on the knowledge graphs, and we keep the rules with high confidence and use the high confidence rules to generate new triplets and add them to the knowledge graph. So we obtain a new knowledge graph. After the root mining, we design our model. Our model can be split into two parts, single models and an ensemble model. Our single model consists of an encoder and a decoder. For the decoder, we directly use complex, as it is the best among the best. It's the best among all the decoders we have tried. For the encoder, we actually mainly focus on the fusion of embeddings, Roberta embeddings and shadow embeddings, as Roberta embeddings actually reflect the text information of the entities and relations, and shadow embeddings actually reflect the structural information in the graph. So I believe the appropriate fusion method is critical to the improvement of the performance. We first use a linear layer to project the Roberta embedding into a small dimensional space, and then concatenate the projected Roberta embedding with shadow embedding as the input of our designed MLP. Our MLP is a single layer MLP with a ReLU activation function. Note that in this MLP, we decided that the hidden dimension is 3000, such that we could learn a very powerful nonlinear function to fit this task. After the MLP, we applied the idea of residual connection that directly add the shadow embeddings to the final output. And we also add a scalar parameter alpha so that it could be learned to control the range of the shadow embedding added to the final output. We believe this residual connection works because it actually constructs an ensemble method in the feature, which is then used in the final prediction of complex. So after we have designed a single model, we ensemble several single models to obtain an ensemble model. For a given set of candidates, we train the single models with different random seeds. So we may obtain different results based on different single model. We then apply the simple average. We average the scores to obtain the final output, such that the final output could reduce the variance that is inevitably included in the single model. This ensemble model also proves to be very effective in improving the performance. After the ensemble method, we develop another technique, which is very similar to the knowledge distillation in recent years. So actually, when we are given a query H and R, we decided to predict the scores of the tail candidates as T. So we directly use the ensemble model to make predictions. After we have made predictions, we allow we distill the knowledge into several new single models, such that the single models could learn the knowledge learned by the ensemble model based on the query. When we have learned the single models, we ensemble these models into a new ensemble model, and then continue to process the iterations for several iterations, such that the performance on the validation data set converges. So actually, the ensemble model can be seen as a teacher model, and the single models on the new iterations can be seen as student models. We then show the experiments of our model design. We here list several designs on the encoder and decoder designs. So the performance here actually shows that based on our design of encoder, we actually improve the performance on the validation data set from 0.0 from 85.6 to 92.6, which is very very amazing improvement on the performance. So we then also show the performance of the ensemble method and the knowledge distillation method. Here, I need to explain that the stage I means that the performance of our model after the I is knowledge distillation. As we have mentioned before, the knowledge distillation actually repeat for several iterations. So the stage 0 actually means that we have no knowledge distillation. So here we have shown that the single model, the performance of single model is 92.6, and the MR of ensemble model is 95.3. So the ensemble method actually improves performance of 2.7 on the MRR. So we also show that how the performance increases according to the iterations of the knowledge distillation. We tried 3 iterations, and the final performance on the validation data set is 97.8. This is our best performance that includes single models, ensemble method, the rule minor, and the knowledge distillation. So our final MR on the test data set was 97.02. It was a bit lower than the performance on the validation data set. Yes. Finally, I'll make some conclusions of our solutions. First, as we have shown in the multi-description and experiments, the fusion of Roberta and shallow features actually improves the MRR from 85.2 to 92.6 on validation data set. It's really amazing improvement on the performance. So it is surely that the combination of different type of features is important in the link prediction task. And second, the rule mining and ensemble methods improves our MRR from 92.6 to 95.3 on the validation data set, which means that ensemble and rule mining also plays an important role in the model performance. Finally, we have tried the knowledge distillation. Experiments show that this technique improves the MRR from 95 to 97, which is also another huge improvement. Yeah, and finally, more information. Our report is now available on arXiv, and our code is also available on GitHub. And if you have any questions, please feel free to contact us. We also list our email here. Thank you.
Okay, thank you, Jianyu, and thank all of you for the 3 presentations. Okay, let me share screen again. Right, so here I would like to do a summary. Basically, the 3 insights that shared across the winner methods are that first, we can see that an ensemble of different embedding methods really works and can indeed increase the performance. So I guess the first takeaway is that it is always useful to try ensembles as long as you have enough computing resources. And second is that when given the candidates, a nice method will be to really calculate some statistics of the candidates, and maybe filter the candidates that have low node degrees or exist less frequently among all the candidates across all the validation or test triples. And and lastly, besides a KG embedding or using the textual representation, we can further improve the model by doing some message passing on the graph to do embedding smoothing, or doing random walks, or even mining some common rules to further exploit the KG structure. Okay, so basically considering this limitation of the candidate set, that randomly selected negatives are often way too easy, and and also the test performance is already like reaching the upper limit. Like we already have like 97% or 97% test MRR. So an update from our side is that we plan to release a new WikiKG 90 million version 2, which is like brand new and based on the recent Wikidata dumps. And yeah, and notably, so for this new KG, we do not provide the candidate tails in order to make the task more realistic. Yeah, so basically we give the researchers and methods full degree of freedom. Like they can either locate a subset of nodes and generate candidate themselves, or the new methods can even like compare the ground truths against all the nodes on the KG, like if they have a scalable implementation. Okay, so now let's like welcome Huijun and Jianyu again, and let's jump into this Q&A session. Yeah, so I will probably start with like a similar question. Basically, I would like to ask both of you, like, what is the most challenging part to like design method or to work in this WikiKG dataset? Maybe we can start with like Huijun, since you like run top.
Okay, and as we know, this dataset is very large, and so in our practice, we find that previous methods are all developed on the small data sets, and some of them will not have equal or how to say, they will not converge like OT. It cannot converge on this data set. So we have to modify it as a more robust version. And besides, we know that graph neural networks have quite a competitive performance on the small data sets. But in our practice, we also find some problems because the training of these models will take a lot of time. And so this limits our choices of the models. And so we think in the future, we can explore a proper way to make use of graph neural networks. Thank you.
I see. So how long does it generally take to train a single model on your new like the Baidu KG framework?
Pardon?
Oh yeah, I was just because you mentioned that it may take a while, right, to train a KG embedding on such a large KG. So I was wondering that how long it takes to train a single model on the Baidu framework.
Oh, you mean the graph neural networks?
Or yeah, graph neural networks or like a single embedding, because I assume you use like the OTE embedding, also the quaternion embedding and so on.
Okay, we training the OTE model about 5 hours. It takes about 5 hours.
On how many GPUs?
How many GPUs? It takes 2 GPUs.
Oh, it only takes 2 GPUs. I see.
Yeah.
Okay, nice. Okay, then Jianyu, can you share with us your experience?
Okay, I think the most difficult thing that we have met in this computation is 2 parts. The first is that the graph is really too large and it consumes too much memory on the machines. So we actually do not have so many resources to train the model. Yes, and actually we train the model, we train our single models on 4 GPUs, and it takes around 5 hours. Yeah, but actually we can only train 2 models simultaneously on a machine. And it also takes us a very long time and hard work to mine the rules and to ensemble the models and to do the knowledge distillation. So actually the graph is too large and it's very hard work to develop an efficient way to train the models like the usual machine learning methods. So the second, I believe it's also a very interesting point in this computation that this computation provides the Roberta embedding, which encodes the textual information in the of the entities and the relations, which is not so frequently seen in the past papers or tasks in the link prediction. So we believe this also brings challenges to how we could find a better way to better use the different levels of features. Yeah, that's all. Thank you.
I see. Thanks. And also, like regarding the scalability issue, Jianyu, because you mentioned that you guys like basically first mine the rules, right? I was wondering, like, how did you partition the graph? Is that random partition?
Yeah, actually, we have considered many ways to partition the graph, but actually we randomly partition the graph into 5 or 10 parts, and each part may have some overlap to the other graph. We just randomly select several maybe several million edges from the graph and use the graph to generate a small graph. Use the edges to generate a small graph. Although we know that this kind of generated graph is sparse and may not generate all the high confidence rules as we want, but we have no choice due to the computational cost.
I see. So basically you just do like random something edges, right, like for 5 times, if I remember correctly, right? Like generate 5 subgraphs.
Yeah.
I see. And also I was wondering, like, how many edges did you add to the graph using the rule? Because like the graph is already like pretty large, right? So
0.1 billion.
0.1 billion.
About 1/5 of the whole graph.
Wow, I see. That's a lot.
Yeah.
I see.
I have a very quick question to like John. So like, did you use text embedding in your method? Like, did you use
text embedding? Yeah, yes, we concat with the ID embedding and feed it into the linear layer. Yeah.
Okay. So you use the text embedding, but it's kind of similar to the baseline.
Yeah.
Okay, I see. It's a very quick question. Thanks.
Yeah, and another question I have is really like, I wonder what's your thoughts on the candidate set, right? I would like to first like start with a question by asking, like, have you evaluated your proposed method? Like, if you do not calculate the statistics of the candidates and do some sort of pre-filtering, like, what's the performance of your proposed model?
Our proposed model, you can refer to the tables here, and we can see that the node and transit and rotate node, we use 10 models named the node, and we can see the results about 0.91, and we use RPS. Okay, we use RPS with transit and rotate and ensemble all these models together, and we will get about 0.94. Yes.
I see.
Without.
I guess the question is, like, what if you are not given the 1,000 candidates? What if you are required to rank the true entity, tail entity, among all the 90 million entities? Because that's actually how your model is used in practice. And that's what we're going to propose for the version 2 of the dataset.
Oh,
like, do you have any comments on this? Like, currently we are providing this 1,000 negative entities that are uniformly sampled as a result, even if the is located in, for example, the tail should be a place, but our entities, negative entities, might contain like trivial, like people or those kind of very irrelevant entities. But in practice, you need to really choose the true entity among all the entities. So, do you understand what I mean?
Yeah, I understand. We use the candidates in the validation set, and then we get the final 0.97. And if we don't use this part, we will get 0.97 and then 94. And so this part candidates does help us to filter out some irrelevant entities to rank in the final prediction. So this can prove the final results, but in the real applications, we should not use this part and we cannot get such information.
Yes. Do you have any thoughts on how you're going to tackle this issue, or?
Yeah, or like an even simpler question would be like, does your proposed like RPS method still apply if there are no candidates provided?
Yes, we can apply RPS methods. All the models are not related to these candidates. We just use features, statistic from these candidates. Yes, our model doesn't use this part.
But you also like design this type of like relation to tail feature, right? Head to relation feature and so on. Like without the candidate sets, then you basically need to like loop over all the nodes on the graph as a candidate tail.
Yes, we construct two parts of these features. The first is constructed from the training trip days, and the second is constructed from the validation set.
Yeah, then how about you, Jane? Do you have any insights on your method?
Could you repeat the question again? I guess I may miss something.
Yeah, we were wondering because like for the next step, right? You probably won't provide any like candidate set for the validation or test triplets. So we are like wondering like what insights do you have, like, or whether your method can still be applicable in this setup.
Okay, so you're asking that if we do not have the candidates, what should we do to this problem?
Yeah,
is that right?
Yeah.
Oh, okay. I think maybe the appropriate way is to first apply a two-stage method. First, maybe we should find a method to ensure we could select a small candidate set that such that the true candidate, the true tail entity is in the we selected set, such that the recall is actually, I think the first stage we should select a high recall candidate, and the second stage we should rank all the candidates such that the correct one can be ranked in a high position. So I think the real problem is how could we find the feature or design method to realize the first stage goal. Yeah, and maybe that's a really hard problem. So we can use some the edge features or the subgraph features. Well, I haven't tried this. I think this might be an promising approach, I think. Yeah, thank you.
Yeah, I think that's a really good point. Actually, based on our experience, is also that finding a high recall or finding a candidate set of high recall is actually pretty challenging, right? But compared with really doing the final step, finding the like the ground truth tale with high precision. Yeah, so I guess I also have a question for the Baidu team. Like, do you imagine like this challenge can, I don't know, can improve any link prediction model, like use it already, like that already been using Baidu product, if there's any?
Yes, and in fact, we use RPS in our work, and we also demonstrate that it is efficient and can help the learning of our knowledge embeddings, and also this WikiKG 90 million dataset also provided with us data to develop more feasible methods to conduct link prediction.
I see. Okay, so Weihua, do you have any like last minute question?
Oh yeah, I've already asked what I want. Thanks.
Okay, then I guess due to the time constraint, maybe next we will move on to the graph level track, which will be like presented by Weihua.
Okay, bye-bye.
Yeah, thank you, Huijun and Jianyu for the discussion.
Thank you.
Thank you.
Thank you.
Well, actually, this one. Okay, can everyone see the slides?
Yes.
Okay. Yeah. Okay, so yeah, I'm going to talk about this in the final session. I'm going to talk about this graph level track, which is to make prediction over the entire graph. And our goal is to predict the quantum chemical property of molecules. And the conventional approach to this is to use density functional theory, DFT, to solve the Schrödinger equation to obtain the quantum chemical property. So DFT is a really reliable quantum calculation method to solve Schrödinger equation, and it's widely used for drug and material discovery. However, the problem is that the DFT is super time consuming. Typically, DFT has these 3 steps. We have these 2 steps to obtain the property of molecules. Given a 2D molecular graphs, we do some geometry optimization using DFT, which could take hours to obtain these 3D molecular graphs, based on which we can calculate the homolumo gap or other quantum chemistry property. And this geometry optimization is really the bottleneck of a DFT. So our task in this KDD cup is to use graph machine learning to approximate the DFT calculate property based on the 2D graph. And especially we focus on the homolumo gap as the target property, quantum property to predict. So we just wanted to go directly from the 2D molecular graph using graph machine learning to predict the target homolumo gap, which is orders of magnitude faster than the original DFT. And so the data set we prepared is called PCQM 4 million. The data set was originally created under this PubChem QC project by Nakata et al. 2017. And this is one of the largest quantum chemistry molecule data sets. It contains 3.8 million DFT calculated molecules from the PubChem database. Here I want to emphasize the difference to the widely used QM9 datasets. The first one is obviously the scale. Our dataset is 30 times larger, contains 30 times larger number of molecules. And another difference is that unlike QM9, our input is 2D molecular graphs given as a SMILE strings, and rather than 3D graph. And this provides a more challenge because 3D graph actually contains a lot of signal about the target property, and the predicting the target property using 2D graph is practically more useful because we don't need to have any expensive geometry optimization. While in QM9, we need to do geometry optimization in the first place to provide the input, which is very expensive. And so the task detail is like we split the data set according in this ratio, 80-10-10 ratio. And the split was done according to the PubChem compound ID. The evaluation metric is a mean absolute error between the predicted homolumo gap and the target homolumo gap. And we also constrain the inference budget to be 0.1 second per molecule. And this is 4 orders of magnitude faster than the DFT, which is our ground truth target. So we conducted some initial benchmark analysis. So we selected 2 things as baseline models. The first one is a traditional model applying multi-layer perceptron over this feature engineered feature called Morgan fingerprint. Another line of models that we tried is the GNN, more modern GNN-based model, including GCM and the graph isomorphism network. And we also add a very promising trick called virtual node, where we add one global node to allow to the molecular graph so that it can exchange message between all nodes in the graph. And what we found is that the GNN model first outperformed this fingerprint model, and as you can see here. And we also find that if we only train on 10% of the training data, the performance of both a fingerprint model and the GNN model actually deteriorate, which means that the large data is really necessary. However, this accuracy, this mean absolute error is far from chemical accuracy, which is our goal in order to make this really chemically meaningful. We also did a lot of ablation study on the depth and the width of the MLP and the graph neural networks, and we often find that deeper and wider models perform better. So now I'm excited to announce the winner of PCQM4 million track. The first place is a machine learning team from Dalian University of Technology, Peking University, Princeton University, MSRA, and Xiamen University. So congratulations. The second place is a Super Helix team from Baidu. And the third place is a quantum team from DeepMind. And these are the accuracies achieved by the top 3 winners, as well as the 4 to 6 place runner-up winners, as shown here. And in terms of the accuracy, mean absolute error, we see that the top 3 winners really achieve a very excellent performance, making the error decreasing by significant margin. Okay, now we're moving on to the 10 minutes talk from each team. And we again welcome questions from the audience. So whenever you have any questions, please write them in the chat. So first, I'd like to start with the first place winner, which is machine learning team. So please.
Can you see my slides?
Yes.
Okay, so hello everyone. It's my great pleasure to share our solution, which wins the first place in this track. And my name is Cheng Xueying. This work is done during my internship at Microsoft Research Asia. So thanks for the introduction of the dataset and task. And we skip the description here and directly introduce our solutions. We use a new graph neural network called Graphomer and a GCN variant in this computation. In the initial round, we submitted a single Graphomer model trained on the default splits, and where the test MAE loss is already 0.1328. In the final round, we use an ensemble model consisting of 8 Graphomer models, 8 EXPC star models trained by the 8-fold cross-validation, and additional 2 Graphomer models trained on the concatenation of train and validation sets. Our solution achieves 0.12 in terms of MAE loss. You can refer to our paper and report for detailed performance. Now I will introduce our proposed Graphomer model in the following slides. As we know, transformers have achieved great success in a large number of tasks, including natural language processing, speech recognition, image classification, and video understanding. But this model is still not the best choice on the public graph reputation leaderboards. There are many attempts to bring transformer into the graph domain, which can be categorized into 3 types. The first type tries to replace the components in classical GNN by attention. For example, graph neural networks use attention as the aggregator. In the second type, people map graphs into strings and build the transformer model directly on the token sequence. For example, we can transform the molecule graph to the small strings and feed it into the transformer model. There are also some works on directly using transformer on graph tasks. However, we noticed that few transformer-based approaches are ranked on the top in any graph prediction leaderboard. Hence, it is still an open problem that do transformers really perform bad for graph representation learning? And to develop transformer for the graph, we need to first understand the function of components in the transformer model. The transformer model generally has 3 components. The attention model can make all tokens interact with each other. The position-aware feed-forward network can learn the abstractive continental representation of the token at different positions. As these 2 functions does not consider the sentence structure, an additional positional encoding has to be used to encode the word order, like which token pair is adjacent and how far away are the 2 tokens in the sentence. Then if we want to apply the model to the graph data, it is natural to map the token in the sequence to the nodes in the graph. But when we do such a mapping, a natural problem arises. What are the node orders in the graph? As the positional encoding tries to encode the sentence structure information, we believe if the transformer can be applied to the graph domain, the key to success is to encode graph structure information into the transformer model through the comprehensive structural encodings. Graphs are far complicated compared to the sentence, and we propose 3 encodings to encode the graph structural information: the spatial positional encoding, the centrality encoding, and the age feature encoding. The 3 encodings tackle different aspects of the graph structural information. The spatial positional encoding tries to encode how far away are the 2 nodes. Centrality encoding tries to encode whether the nodes is important or not. And age feature encoding tries to encode the age feature information. So first, we propose a novel spatial encoding in Graphomer to capture the structural relationship between nodes. For each node pair, we assign a learnable embedding based on their spatial relation. In our solution, we use the distance of the unweighted shortest path distance between any 2 nodes, which could be encoded as a bias term in the softmax attention, and help the model accurately capture the spatial dependence in the graph. Then furthermore, we add an additional distance, which is the Euclidean distance between any atom pair in the molecule's conformer. Second, we propose a centrality encoding in graphoma to capture the node information, to capture the node importance in the graph. In a graph, different nodes may have different importance. For example, celebrities are considered to be more influential than the majority of the web users in a social network. In our solution, we leverage the degree of the nodes for the centrality encoding, where a learnable vector is assigned to each node according to its degree and added to the node features in the input layer. Besides, we design a new age encoding method to further take the age feature signals into the transformer layers. To be concrete, for each node pair, we compute the weighted average of the age features along the shortest path where the weights are the parameters and then use it in the attention module. So here to summarize, Graphoma is built on a pure transformer model with 3 structural encodings: the spatial encoding, the centrality encoding, and the age encoding. Equipped with these encodings, Graphoma can better model the relationship for node pairs and represent the graph. Then we also show that Graphoma is more powerful than other GNN variants by showing Graphoma can approximate the aggregator of GIN, GCN, and GraphSage. For the details, please refer to our paper. Now we introduce the EXP star model, which is also example in our solution. The core idea is that the aggregation in GNNs could cause information loss. So the EXP star alleviates this problem by expanding the hidden feature and applying the nonlinear units before the GCN's aggregation. The pipeline of the node representation for EXP star model includes the expand, combine, sum, and update steps. So as a summary, in this computation, we give an affirmative answer by showing that transformer can perform well on graph representation task by using proper encoding methods to encode the graph structural information. And in the future, we would like to explore the strengths of the graphoma model on more tasks in biology, chemistry, and even physics. So thanks for listening. We sincerely thank the OGB team for the effort in making this challenge in such large scale. For the model part, please refer to the following 2 papers. And for the source code, please refer to the GitHub link here. By the way, I'm looking for a PhD opportunity in the next fall and going to apply in this autumn. So if it happens that you are recruiting, please consider me. Thank you.
Thank you very much for the great talk. So next, we'll have Super Helix team from Baidu.
Hi, can you hear me?
Yes.
All right. Oh, sorry, I need to exit the Zoom and reopen it to give it preload.
No problem.
Oh, sorry. All right, can you see my slides and my laser pointer?
Yes.
Okay, great. Hi, everyone. I'm the Shanzhuo Zhang from the team of SuperHelix, and we have provided the second place solution of the KDD Cup 2021 PCQM4M. And I'm from the PaddleHelix team from Baidu. Oh, sorry. Okay, I will show you first the timeline of what we have did throughout the challenge. I put this here before introducing details of the model because I think this is more interesting than the details which you can find in our technical reports. All right, in the first month, all we did was very simple. We just tried to understand the background of the task. In the first 1 week or two, we were struggling to understand what is the homolomer gap and what is DFT. It is quite difficult for us because none of us team members know anything about quantum chemistry before this challenge. And we did this because we believe that when we constructing a deep learning model, understanding the properties of the dataset is really more important than optimizing the model structure itself. And at the same time, we also ran the baseline code of the baseline code provided by the OGB team. And we found that the hidden size of the model should be large and training on a single card is too slow. So this is conflicting because we need a large hidden size of the model, but training on a single card is too slow. So we have to find a way to train the model in a distributed manner and to speed up our investigation. So in the following 1 or 2 weeks, we just do some engineering to speed up the investigation with distributed training. And then in the second stage, from the April 15th to before the first submission, we focus on optimizing the backbone of our GNN and tried more features to select the useful ones, which I will give you more details in the following slides. Also, we did very naive example before the submission. We just averaged the predictions of 2 models of our 2 best models. Then the MAE decreased about 3,500. And the first submission on the 5% test set, we got an MAE of 0.1294. And then in the last month, we ran DFT ourselves to generate accurate 3D molecular confirmation. We did this because based on the background of the task, we suppose there is a strong correlation between the molecular confirmation and the homolomer gap. And with the confirmation, a question comes up, is how to design the auxiliary tasks, how to make our model learn from the 3D molecular confirmation. And then in the last week before the final submission, we just did some cross-validation and ensemble more of our models. And in this part, we will introduce the feature we have tried. We know that OGB has provided many features which are very useful. And besides that, we tried some extra features such as the range sizes, which means the size, the range size that a node resides. So it's very, very difficult to say. And the partial charge, van der Waals radius, valence of oxide, number of hydrogen. And these features we think are related with the task itself. And we have also tried some features, but found they have no effect such as the average atomic mass, average number of bonds per atom, and so on, many other features. And there are also features that was abandoned by us because we found either they are difficult to implement or the definition of them is ambiguous. So then let's see how we use these features in our model. There is a problem of feature embedding here is that we have some float features. Just as we show here, there are expanded distances, there are van der Waals radius. These features are floating point features. So if we just put these floating point features and concat them just at the end of the node embedding, we will find the model be very heavily fit into these overfit into these floating point features. So what we did is to use this technique called Gaussian expansion, which is from a previous literature. We manually selected n Gaussian basis functions with uniformly spaced mu's and the same sigma. You can see from this figure, a floating point feature comes in, and this floating point will be expanded to n floating point values based on the values of these n Gaussian functions. And then these n floating point values will be go through another linear layer to transform it with the same size with the integer embedding and then add them together. We tried this and found that new features and plus the Gaussian expansion improved the model by 4 in 1,000 in the MAE. Then is the second part of the model structure, the backbone and auxiliary tasks, which we names our model light gem. We use a quite normal GNN message passing scheme, which is shown on the upper right of this GNN block. The key point to say is there is a non-linear layer in this message passing procedure. We concatenate all the three features from the source node, destination node, and the edge feature between them, and go through an MLP. And this non-linear layer in this message passing procedure improved the model by up to 1% in MAE. This is quite significant improvement. We also tried smoothing, a smoothing technique, which is also known as the APP-NP, and get a slight improvement. And the second thing to say is we designed 3 auxiliary tasks. The first auxiliary task is the context prediction. With this task, we expect our model to learn the local topology of molecules. This task is very similar to what Wei Hua has proposed in his pre-training GNN paper, but our implementation is a little bit different and more simple. We just make a string from the node context, then hash the string, and then merge it to a single bit as a task label. If you know the Morgan fingerprints, you may find this this was very similar. Just use a hashed bit to represent a local structure. By this context prediction, we improved the model by about 2 in 1,000. And the last 2 tasks are to predict the bond length and the bond angle. Bond length and bond angle are only reasonable extracted from 3D conformation. But we believe this is important because molecules with same topology may have may be different when seen from the 3D perspective. As an example, we can see from this figure, these 2 molecules are the same in topology, which means they cannot be differentiated by the GNN model itself. But in the 3D conformation, they have different bond angle, they have different bond lengths. So in the 3D conformation, you can easily distinguish these 2 molecules. And this information must be useful in the chemical space. And the next question is why we learn the accurate 3D confirmation. The first answer is that we believe we learned the DFT and we believe that there is strong correlation between the 3D confirmation and homolumen gap. And we believe that this confirmation must be accurate because the homolumen gap is quite a small value and may be very different with different confirmations. And the second answer is we also tried inaccurate 3D confirmation, which is generated by the RDKit or OpenBabel and find no improvement. To ensure the accuracy of confirmation, we simulated all the 3.8 million molecules with just one round self-consistent field DFT. We cannot do more because it will cost too much CPU time. And we just filter about 20% simulation results, which were comparable with the PCQM dataset itself. Finally, we found that learning the bound length and bound angle improved the model by 1.5 in 1,000 based on the other techniques. So this is an extra improvement. Yeah, thank you for listening. This is our team members. We are from the Petahelix of Baidu and PJL of Baidu. And welcome to watch our GitHub repository. Thank you.
Thank you very much, Sanzo. Very good, great talk. Finally, I'd like to welcome the quantum team from DeepMind.
Hi, can you hear me and see me?
Yes.
Great, thank you. So hi everyone, I am Álvaro Sánchez González, a research engineer in DeepMind, and I will be presenting our winning entry on the PCQ track of the OGB large-scale challenge. So of course, this was a team effort, and I am presenting on behalf of all of my fantastic colleagues that were part of a team for this entry. So I want to send a big shout out to Ravi, Peter, David, Andrea, Johnny, Sibon, Jacqueline, Shantanu, and Peter. Also, a big thank you to the fantastic organizers of this great competition. It was great to participate. So in the next slides, I will describe our solution and some interesting results. But before going into details, just a brief reminder that all of the details of our models and results that I will be presenting today are available in our paper, and the code is also available in a GitHub repo. Both paper and GitHub repo include details about both our winning entry in the PCQ track and also in the MAC track. So I recommend you to check it out. So at this point, I guess everyone is familiar with the PCQ task, which consists of predicting the homolumen gap for a test set of about 400,000 test molecules. And you know, the challenge is to be able to approximate DFT, which we usually take hours in a fraction of a second. So our approach to solving the problem was to use some of the techniques from our recent work on graph neural networks for learning simulations and molecular applications. If you're not familiar with this work, I invite you to check the references from this slide. And as we will see later, the main ideas we leverage are deep graph networks with tens of message passing steps, the encode process decode approach for designing models, and also auxiliary denoising objectives to avoid over-smoothing and prevent overfitting. We implemented all 5 ideas using JAX and our open source ecosystem around it. For those not familiar with JAX, JAX is a functional Python library designed for high-performance numerical computing, which enables rapid experimentation with an API similar to NumPy. Specifically, we have used Giraffe, our library for graph neural networks in JAX. And I recommend you to check out these libraries and try them in your next project if you like them. Now, getting to the actual model. In our case, we went out the obvious route of building a graph where each of the nodes is an atom. And we simply use the provided features such as atomic number, chirality, etc., specified as one hot. Then we build bidirectional edges according to the bonds of the molecules, and we also encoded the provided Borg properties as one-hot features again. Finally, we also used RDKit to compute a conformer, at least a raw approximation for each molecule. And given the conformer, which we augmented with random rotations and mirror transformations, we use the relative position between pairs of atoms as an additional edge feature. And it is worth noting that RD-Kit was not able to produce conformers for a small fraction of the molecules. So in the end, we ended up training models both with and without positional features. As mentioned before, the architecture of the model is based on the encode, process, decode framework. And as you will see, rather than to design a highly specific model, we try to keep the actual model as simple as generic as possible, so it can be reused in any other domains. So the encoder simply uses MLPs to encode the node and edge features into a fixed size latent space for edges and nodes. And in this case, because we did not use any global features, we simply initialize the global latent state to zeros. Then the processor is based on graph networks. Each graph network performs a step of message passing and global pooling to update the edge, node, and global latent states. So specifically, a new edge or message view is computed for each edge using an MLP. These messages are then aggregated with a summation and used to update each node with another MLP. And then finally, all nodes and edges are pooled, also with a summation, and used to update the globals with a third MLP. And then the actual processor consists of a sequence of identical graph networks, but each with their own weights, connected with residual connections to enable gradient propagation. And as you can see, the core of the model is conceptually quite simple. Then finally, the decoder uses another MLP applied to the pool nodes at the output of the processor. And this extracts the global predictions for the HOMO-LUMO gap. It also has a couple of per node and per edge auxiliary outputs that we use for the auxiliary denoising tasks, which I'll explain in the next slide. For the main loss, we use mean absolute error between target and prediction, as this was the competition metric. And as mentioned before, we also implemented an auxiliary denoising task for nodes and edges. So the idea goes as follows. First, we take the input one-hot features for some of the atoms and some of the edges and perturb them with noise. And this can result on, for example, changing some of the atomic number, species, and other properties of the atoms. Then we give this molecule with noisy features to the model, and we ask the model to correct the features via the auxiliary per node and per edge outputs. That is, we ask the model to predict the correct atom and bond properties. So we train the model to do this by adding an additional cross-entropy loss. And as we will see later, these additional denoising objectives can really improve performance. Then we use several other standard techniques, such as target normalization, dropout, learning rate annealing, and exponential moving average of the model parameters for increased performance. We also trained with a large batch size of 512, which was easy with JAX, as we could seamlessly distribute the training across 8 TPU cores. And then, while we did all of our model fine-tuning by training on the training split only, for the final test submission, we also wanted to train on part of the validation dataset. So specifically, we implemented a 10-fold approach, where each model will train on all of the training data and 90% of the validation data, and leave the other 10% of validation data for cross-validation and early stopping. And then we trained 10 different models, such as the left out 10% of validation data was different for each of the models. Then we assembled all of the test predictions using a median for all of these models. And in fact, we actually trained 2 seats for each of the models in this 10-fold configuration. So in total, we assembled 20 models. And as I mentioned earlier, not all of the molecules have conformer features available. So for our final submission, we trained 2 models, one for test molecules with conformers available, and the other one for those lacking conformer features. And each of the models had slightly different hyperparameters. For example, the non-conformer model was deeper, but otherwise they had the same architecture. Each of the models had about 225 million parameters, which adds up to 10 trillion parameters in total, if you take into account both models, the 10-fold and the 2 seats as ensemble. So with these models, we achieved a 0.1205 test MAE, which left us third place winners by a very, very small margin. So finally, I want to quickly show a few ablations, which emphasize some of the key modeling choices. So for these ablations, we trained 5 seats of a single model on the training split only, and show learning curves for the validation split. The first thing we tried to remove was the auxiliary denoising objective. When we did this, the model performance decreased by about 0.003 MAE. So for comparison, this is about 6 times the difference between the first entry winner and the third entry winner. We speculate the reason is that the auxiliary per node and per edge denoising task prevents overfitting and helps with oversmoothing on very deep networks. We also tried to remove the conformer features from the conformer model. And in this case, the decrease in performance was about 0.001 MAE, still twice as much as the difference between the first entry winner and the third entry winner. The third obvious comparison was the depth of the GNN. So for the conformer model, we used 32 message passing steps. And if you decrease the number of steps to 16 or to 8, the performance decreases as much as 0.01 MAE. However, if you increase it to 50, then you start seeing some overfitting. In fact, when we ran a finer scan of the competition submission, we found that 40 message passing steps was slightly better than a submitted model with 32 steps. So that was a missed opportunity. On the other hand, for the non-conformer model, we found less overfitting, and we found that we could go all the way to 50 message passing steps without observing overfitting. So this is what we use for the competition. Finally, we made a couple of changes to the latent size of the model and the hidden size of the MLPs. And we found that a small latent size with a larger hidden size was beneficial. And we speculate this is because the smaller latent size is more effective preventing overfitting. And also the model with the large hidden size has more parameters, which may help optimization. So to wrap it up, we believe that graph neural networks have a great potential in scientific applications. And of course, as we get better at training very deep GNNs, using general purpose strategies such as encode, process, decode, and noisy nodes, the impact of these types of models will continue expanding. So thank you so much for your attention on behalf of our team from DeepMind. And please check out the additional resources, including our paper, our GitHub repo, and all of the open source libraries. Thank you.
Thank you very much, Alvaro. Great talk. Now I'm going to briefly summarize the solutions by the winners. And while I'm doing this, please, for the audience, please write any questions you have to the chat so that we can move on to the question and answer session after my talk. So just to summarize the solutions, I found 3 common trends among the winners. 3 things are: use even bigger models helps, and use global message helps, and use 3D structure helps. So in terms of the bigger model, our baseline, initial baseline was only using the 5-layer GNN, while we find the winners use 11 up to 50 layers, which is much larger than what we've used. And the number of GNN parameters accordingly increased by a large margin. And it's a kind of an interesting trend that on the big data set, the bigger models indeed perform better, similar to what the computer vision NLP community sees. The second trend is that all the winning solutions use this global message passing, where GNN message passing takes all the node embedding into account, not only its neighbors. So virtual node is what has been presented before, and the Graphformer also do this interesting global message passing using fully connected graph. So these tricks seem to be very promising. The third one is all the solutions use like a 3D structure of the molecule, even though we only gave a 2D structure. And the intermediate, this 3D structure is calculated with cheaper geometry optimization, either using RDKit or one-step DFT optimization. And they use the winners use the structure as a self-supplied signal, or use this 3D signal directly as an input to the model, and they seem to really help. And yeah, as we're going to announce later, due to this, we're going to release a new PCKM dataset, which we provide the ground truth DFT calculated 3D graphs only for training molecules, so that there might be, this Baidu team do not need to calculate this from scratch, but these are actually obtained together with the homoluminal gap. So there's no reason for us not to provide it. So we're going to provide this as an additional signal for people to explore. yeah, so with that, that's my conclusion. And now let me see the question answer session. Okay, maybe I will first start with my question. So my question is like, again, this is our intuition was that the bigger model benefit more from the bigger data set. And I'm wondering, did you find anything that works for the medium scale, for example, OGB data set that that doesn't work for a small data set that suddenly start to work on large scale data set, or vice versa? This is to all the kind of speakers. Is there any trick that that only works on the large data? Anything that you find, or is it like a similar architecture basically perform well on both small data and large data? So let's start.
And maybe I can start.
Yes. Yeah, please.
Yeah, actually, we try to do some initial exploration on using transformer to the graph data on early of this year, because we see that the transformer model has achieved state-of-the-art performance on computer vision. But unfortunately, we get failed because we use the transformer model on the small scale data, and we find that the model is very easy to overfit. And so I very like this large scale challenge, because it's a very good platform for us to test the new model architectures. And actually, in the beginning of the experiment, we quickly find that the transfer model can beat all the baseline models in the OGB large scale data set. And so we know that this model architecture will work, and just try to explore a more advanced method to improve the model. And another thing I want to share is that after we trained this model, we use it as a pre-training checkpoint and directly apply this model to small scale tasks. And we find that by fine-tuning this model checkpoint on small scale data set, and we find we can get a very strong performance, like in the standard OGB task. Yeah.
That's interesting. By small scale, like which data set do you mean? Like, is it small scale quantum data set, or is it small scale?
It's a ZINC data set and some other small scale quantum chemistry data set. I think we have tried more than 3 different data set like for chemical classification, and we find that by using our model checkpoint on this large scale data set, the model trained from this OGB-LSC data set, we use it as a starting point to fine tune the model. We can get very strong performance.
Interesting. Does it also transfer to like a drug discovery data set, like a PCBA data set, like those bio related data set, or is it mainly transferred to the quantum?
Yeah, we tried the PCBA data and we achieved better performance.
Oh, interesting. Because quantum and bio are so different. So just wondering.
Our fine-tuned graphomer surpassed the best model by a large margin in the PCBA data set, which is biology data set. Yeah.
I see. And did you perform?
Yeah, and several days.
Oh, no, go ahead. Go ahead. Sorry.
And several days ago, there's some other teams that start from our checkpoint and fine-tune the graphomer on the HIV along with the Morgan fingerprint features, and they achieved very strong performance, ranked in the top 3. Yeah.
Very interesting. Very interesting.
Yeah, so I think use pre-trained model on large scale data and apply it to small scale data should be a trend, or some new things need to explore in the future for the graph domain. Yeah.
Thank you. Thank you for sharing. That's interesting. Interesting insight. How about Sanjo? Do you have any comments on like using like something that do not work on medium scale, works for large scale, or you find like the same model works for both? Or
Yeah, we are still trying. We're still trying on the HIV dataset and PCBA. And we have already seen the paper from the Graphomer team, and they have a very impressive result on the PCBA leaderboard. So I think we need more. Our model can be transformed to the PCBA data set, and we have tried small hidden size and get better results than the model we submitted before on the PCBA leaderboard. But we still not have better results than the Graphomer. So I think for small molecules using GNN or transformer like structure, which is better, is still controversial, I think. Yeah.
Mm-hmm. Thank you for the comments. Alvaro, do you have any insight or comments?
So just generally, as I said, we sort of like try to keep the model very similar to the sort of model that we use in smaller data sets, and perhaps the only thing that we fine-tuned a little bit more was the auxiliary task and the relative losses, and of course the depth of the model. So in that sense, we just found that like because it's harder to overfit to a larger data set, you can increase the model and then you can get better generalization to the test data set. But like beyond that, at least we didn't notice any major qualitative difference between what we had to use.
Right, I see. Actually, regarding this DeepMind solution, I find like personally, I train like a deeper like a graph isomorphism network, and I find the training is super unstable, and it's like training this 50-layer GNN. It's kind of impressive to me. Have you ever observed any training difficulty or yeah?
So one of the slight difficulties that we found is that like one of the things that we removed from our network that we usually use is a layer norm layer. And the layer norm layer really helps into kind of like making training much more stable if you normalize your data. However, in this case, it was decreasing performance. And this was a tricky bit because after removing the layer norm, the sort of scales of things were sometimes getting out of hand. So like the deeper your model, the larger your initial loss, if you wish. So it was sort of kind of like harder and harder to start the beginning of training. But like at the end of the day, we found that models will still be able to converge to something. It was just like it would take longer to train than usually it takes with a layer norm. But beyond that, I think the auxiliary tasks really helped sort of regularizing the model. And we didn't really observe, like, I think later in training, some of the learning curves have some noise, but as you could see in the plots that I was showing before, learning curves are quite clean once you fine-tune the parameters.
Right. I see. Do you have any intuition why your auxiliary task and this depth, kind of how they interact with each other? Why like this auxiliary task, like denoising term, has something to do with the depth?
So we believe that the denoising terms helps because of two reasons. The first reason is because it prevents overfitting. At every iteration, you're feeding data that is slightly different because you're modifying your input features. So now you have like an infinite size data set, if you wish. And now the second reason is because this is only a global prediction task. Some people have reported in the past that when you only make a global prediction, your model starts having over-smoothing, as in all of the node features start converging to the same thing. And then more message passing steps don't really help you. So by adding a per node auxiliary task, you prevent this from happening because those representations need to continue being different.
I see. Interesting. You kind of retain the original input information to the last layer. I see. That's very interesting. Thank you. Let me look into the question by the audience. Okay, Matthias, maybe you can ask a question directly.
Yeah, sure. That's possible as well. Like, yeah, my question would be like, what is your take on global pooling methods to obtain graph level representations? Like, I see that most methods are using some aggregation, and I was wondering, is that all we need for molecules, or like, is there still some research to do to obtain better graph level representations? yeah, please go ahead.
So perhaps I can give my short answer. So at least for this, my intuition was that the mean was going to work better because the homolumo gap is not meant, I don't think it's like something additive that, you know, as you add more atoms, you add your homolumo gap or smaller. It's more kind of like a complex distributed function. However, when we tried mean aggregation, it was like clearly worse, at least in our case. So we defaulted to sum. We didn't have time to think too hard about why there was a risk.
And any opinions on using attention or stuff like that?
We use virtual node because, to be honest, I'm a researcher in natural language processing and just stepped into the graph domain from last year. So in natural language processing, the popular use way is to add a virtual token at the beginning of the sentence. It's called the CLS sentence. And then like invert the CLS sentence, the output of the CLS sentence. The CLS token will be used as the representation of the sentence. So here in graph, we use a virtual node and we view the representation of the virtual node as the representation of the graph. So we don't use the global pooling, but we use additional virtual node. Yeah.
Okay, I see. Thank you.
Thank you. I have this quick question from audience for the first place winner, machine learning team. The centrality feature, is it derived from the degree matrix only? Do you need to calculate the eigenvectors from a adjacency matrix?
No, we didn't use the eigenvector of the adjacent matrix. We directly use the node degree feature, but I think it's an alternative strategy. Maybe different kind of centrality measure can be also explored in the future.
I see.
Yeah.
And do you have any sense of how sensitive it is to this positional encoding? Does adding more help, or is it kind of already saturated the performance?
I'm not sure. Yeah. I think we have tried many ways to encode the graph structure data, the graph structure, and we find that some of them give very similar performance, but some of them may downgrade the performance of the model.
I see. I see. Interesting. Okay. Guess any other questions from the audience? Okay, if not, we can close the graph level session. Thank you very much for the great presentations, and congratulations again for the winning this competition. Finally, let me just present one update from OGB large scale challenge team. So the future plan. A very short one page slide, but yeah, it's so the challenge, the datasets were originally designed for KDD Cup, but due to a lot of interest from the community, we're going to release the public leaderboards. Hopefully will be up next month, so that community can still continue to explore the new methods on the dataset, and we still hide the test labels. For the test set, we're going to split the test set into two sets, test dev and test challenge. And basically test dev will be used for our leaderboard, which people can evaluate on like a weekly basis. While for test challenge, we're planning to use it for future competition. So people can only touch it at the future competition if we're going to hold any. In terms of the datasets update, based on the lessons we've learned from the KDD Cup solutions, we're going to have two updates on the dataset. The first one is on the link prediction dataset. We find the model performance already saturated during the KDD Cup, so it's very impressive. We're planning to make this task more challenging and realistic by not providing any tail candidates as presented by Hongyu. In terms of the PCQM, we are going to fix some of the small bugs on the dataset. There's a small a mismatch between molecules and their properties. It kind of minor affects 10% in a minor way of the entire 10% of the total molecules. And the way it affects is we find the the initial smile strings, after geometry optimization, actually the smile string changed. And the smile string that we provided is the initial smile string, but from chemistry perspective, we should have provided the smile string of the optimized like the geometry. So we're going to fix that bug and release the new one soon, hopefully next month. And also, because we find a lot of winners actually utilize 3D structures, we're going to release this 3D structure, like a ground truth 3D structure information, only for training molecules, so that model might use this information during training. At test time, we still want people to predict based on 2D molecule structure. Yeah, that's all from us about the future plans. And tomorrow we are going to have like an invited keynote session and panel discussion discussing the next step in graph machine learning research. So please attend it. Yeah, that's all from us. Thank you everyone for attending, and hopefully see you tomorrow.